Good day, everyone, especially to our Professor Sir Christian Caben Laresma. Good afternoon, sir. My name is Susana E. Devota. My topic for this session is about unique factorization theorem. To start with, let me introduce first my intended learning outcomes or the ILOs. At the end of the session, the mathematics students should perform unique factorization. In number theory, the fundamental theorem of arithmetic, also called the unique factorization theorem or unique prime factorization theorem, state that every integer greater than 1 either is a prime number itself or can be represented as a product of prime number. X is an element of the sets of all positive integers such that x is greater than 1, where number x is a product of p1 times p2 times p3, so on until pn, where p is a prime number. Example, 30 is a number greater than 1 and can be represented by a product of prime numbers such as 2, 3, and 5. The list of factors can have the same prime number in it more than once. Example, the factor of 100 is equal to 2 times 2 times 5 times 5, or 100 is equal to the square of 2 and the square of 5. Notice that the prime numbers 2 and 5 were repeated twice. If you change the order of numbers in the list, it's still considered to be the same list. Example, for number 1000, the factor of number 1000 are 2 times 2 times 2 times 5 times 5 times 5. Can also be written as 1000 is equal to 2 times 5 times 2 times 5 times 2 times 5. This means that the orientation of the prime factorization does not affect the value at all, as long as it contains the same prime factors and the same number of its factors. Unique means that is only one possible list of prime number factor for any original number. For example, the number 150 can only have prime factors of 2 times 3 times 5 times 5, and no number has the same prime factors and number of its factors. I have here an example of prime factorization. Since unique factorization is also called as a prime factorization. Using our factor tree, we take number 100. Number 100 is divisible by 2. We take 2 as our basic divisor. 100 divided by 2 is equal to 50. 50 divided by 2 will give us the quotient of 25. Then the factor of 25 is 5 and 5. So the factor of 100 is equal to 2 times 2 times 5 times 5, or can be written as 100 is equal to the square of 5 and the square of 2. Another example, we have the number 100. The number 1000. The number 1000 is an even number. So 1000 divided by 2 is equal to 500. 500 is divisible by 2. So 500 divided by 2 is equal to 250. 250 is divisible by 5. So 250 divided by 5 is equal to 50. 50 is divisible by 2. So 50 divided by 2 is equal to 25. And the factor of 25 is 5 and 5. So the factor of 1000 is equal to 2 cubes times 5 cubes. The last example is 990. 990 is also factorable by 2 or divisible by 2. So 990 divided by 2 will give us the quotient of 495, and 495 is divisible by 5. 495 divided by 5 is equal to 99, and 99 is divisible by 11. 99 divided by 11 is equal to 9. The factor of 9 is 3 and 3. So the factor of 990 is equal to 2 times 5 times 11 times 3 times 3, or 999 is a product of 11 times 5 times 3 times 3. Although it seems easy to factor an integer, it is actually not always. Generally, if the number has only small factors, then it is not hard to factor. But if the number is very large and has only few large factors, then there is no efficient algorithm clearly available. For the evaluation, we have 5 numbers for our evaluation. Thank you and God bless.